In the following 4 slides, we're going to talk about different measures of a binary tree. Let me switch to iPad for the entire discussion. And the first measure we're going to talk about will be the number of nodes. The second one, the height of the tree. The third one, the number of external nodes. And the last one, the number of internal nodes. For each of the measures that we're going to talk about, we want to derive the lower bound and upper bound for that particular measure. Let's now start the discussion one by one. The first one will be the number of nodes. What will be the lower bound and what will be the upper bound? So the context will be given a binary tree with height h, and of course our implicit assumption is the value for the height will be larger than or equal to 0, just not negative. And you can see that the value for the number of nodes will be just n over here in the middle. And what will be the lower bound? This will be the lower bound, height plus 1. And this will be the upper bound, 2 to the power of h plus 1 minus 1. Can you see why the lower bound and upper bound are such the cases? Let's now first use some example height value, let's say 3, small enough to really illustrate the lower bound and upper bound. In this case, if the height is only 3, in that case, what's really the minimum number of nodes? Well, in order for the height to be 3, that means at least there should be one node which has the maximum depth from the node itself to the root. Meaning that, let's say if this is the root of the tree, and then there should be at least one node for which it has the depth 3. 1, 2, and also 3. Right? You can see here we got exactly 1, 2, and 3. And we have no other nodes. So that's really the minimum, right? The minimum really means we need to have that node to really have the depth 1, 2, and 3. And no other node will be added. If you really add another node, for example, over here, that would not be the minimum anymore. And how do we generalize this? To really generalize this is quite easy. You can think about the general case would be when we start with the root over here, and then this will be the first edge to really go towards that particular node with the depth h. So we're going to go all the way over here and to here. This will be the node over here. In that case, how many edges we have? Well, it will be exactly h edges. And with h edges, how many nodes exactly? We got 1, 2, 3, 3 edges corresponding to 3. How many nodes do we have? We got 1, 2, 3, 4. The beginning and the end, right? So that's going to be the h plus 1. That means the h plus 1 nodes over here. That's how you visualize about the minimum case, right? So that's the h plus 1. Just remember it's h plus 1, not just h, because you have to make sure you cover the node itself with the maximum depth h and also the root. Let's now talk about the maximum case. The maximum case is something you're pretty much familiar with, but let's still do it quickly. In the case of h being 3, in that case, we want to make sure before we reach the depth of 3, we got maximum number of nodes at every level. Level 0, we just got the root. Level 1, we got 2 nodes over here. Level 2, we also got 2 children for each node. And level 3, we actually got 1, 2. And also 1, 2, and also 1, 2, and also 1, 2. As you can see, the maximum depth for the nodes at the bottom level will be 1, 2, and 3 over here, right? And in that case, how many nodes do we have? Let's verify that. It's going to be 2 to the power of h plus 1 minus 1 according to the formula. This is also something we derived earlier, which will be 2 to the power of 3 plus 1 minus 1, which will be 15. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Right? So this number is really matching. How do we generalize this? The way to generalize it will be, let's say this is our general tree, where we got the heights, let's say starting from the root all the way to the bottom over here, right? So this will be h. And we want to make sure we got the maximum number of nodes starting from the root over here all the way down to the bottom over here. So we got the maximum number of nodes filled out at each level. So it's going to be 2 to the power of 0 plus 2 to the power of 1 all the way to 2 to the power of h, which will be at this level over here, right? This will be h, 2 to the power of h, which will be exactly this number over here by applying the geometric sequence sum formula. 2 to the power of h plus 1 minus 1. Notice that we got from 0 all the way to h. We got h plus 1 terms. That's why. Alrighty, so that's about the minimum and maximum. It's more like a warm-up, something you may have already known, especially for the maximum. Right, let me just highlight it. So this will be the maximum in the general case, and this will be the minimum over here in the general case. Let's now move on to the second measure. In the first measure, we fix the heights h, and we try to see what the lower bound is and upper bound is for n. And for the second measure, we kind of swap these two variables. And in this case, we're talking about the height of the tree. How can we derive the lower bound and upper bound? So now, given n nodes, what will be the heights, right? Again, so here you can see, obviously, n should be larger than or equal to 0. And then the heights, which will be in the middle, and the lower bound will be, let me use green here. This will be the lower bound for the heights, and this will be the upper bound for the heights. And you can feel free to pause the video and think about why the lower bound and upper bound for the heights will be like these two. Alrighty, let's now talk about the maximum. I think the maximum might be easier to understand. And for the lower one, we need to do a little bit of derivation using log. Let's see the maximum first. We say that given the number of nodes being n, and the maximum height we can have is simply h. We have seen such tree already, right? You can see, remember this one here? This is so-called a one-path tree. Let me write it down. One-path tree. And there is a little remark I would like to make, actually for the earlier case. And this is one way to really slant the tree. You can always have the left, and left. Right, make an annotation over here. This will be the left, and left. In order to really create this one-path tree, you can also say right, and then left, and then right. That's also fine. But just for simplicity, I just gave you a one-path tree which will always slant the same way. Let's now go back here. What will be the maximum heights? In that case, well, let's say if n is equal to 7 over here, in that case, the maximum heights will be when we actually don't waste any nodes in branching. We just go exactly one path. That can really make sure we got the maximum height, right? The maximum will be don't waste any nodes branching in two ways. That's how I thought about it informally. Branching two ways. And let's see exactly how we can visualize it. Don't waste any nodes. Branching two ways. So let's say we start with, this will be the root, and then we got exactly 7 nodes. 1, 2, 3, 4, 5. Let me just try to draw better. Right? I just need a little bit more space. 1, 2, 3, 4, 5, 6, 7. All the 7 nodes. And let's say they're slanted just the same way. In that case, what would be the maximum heights? Well, that means we're going to count the number of edges, right? In that case, 1, 2, 3, 4, 6, 5, and 6. So the number of nodes is actually equal to 7, in which case the height will just be exactly n minus 1, which will be 6. Exactly 6 edges that we have counted. Right? So that's just one example. So the way for you to really reach the maximum height is by slanting, for example, the child in the same way, all the way throughout. In that case, you are not wasting any nodes branching out two ways. What about generalizing it? Very easy. You can think about if you start with the root over here, and then you're just going to slant maybe the same way until over here, right? Over here. And how many edges do we have over here? In that case, we got exactly n minus 1 edges. Because we got n nodes, We got n nodes, including the beginning and also the end. So it's going to be n minus 1 edges, right? Just remember, in order for you to have connected nodes, in that case, the number of nodes is always 1 plus the number of edges. Or symmetrically, the number of edges will be always 1 minus the number of nodes, right? It's very important for you to remember. That's about the maximum heights. What about the minimum heights? The minimum heights will be the opposite. You really want to branch out whenever you can, so that you can really minimize the heights. It's really the opposite strategy that we are taking. In that case, branch out 2 ways whenever possible. Whenever possible. That'll be the strategy. Let's say we start with the root, and we're going to branch out whenever possible. So we're going to branch out 2 ways over here. So we get to level 1. And we're going to branch out again for every node whenever possible. You can see that's exactly the strategy for maximizing the number of nodes at each level, right? It's really happened to be the same strategy for really having the minimum heights. And we got 7 nodes already, right? We got 1, 2, 3, 4, 5, 6, 7. And what's the heights over here? You can see 1 and 2. So height is just equal to 2. Is this number really matching what the formula, the lower bound, tells us? Let's check. According to the lower bound, it's going to be the log base 2. And then n plus 1, which will be the number of nodes, 7, 7 plus 1. And then subtract 1 from there, which will be equal to log 8, 3. 3 minus 1 will be exactly 2. You can see this is really matching the heights over here, which happen to be the minimum. How do we generalize this? The way to generalize it is to really to do some derivation. Let's do it together. Let me now use the purple over here. We know that this kind of a structure is really going to be the case where you got the minimum heights, right? This is really the structure. And let's make it a little bit more general over here. So this will be the general case. You can see the height is from here down to over here. The height is actually h. How many nodes are there? In this case, we know very well the formula is going to be 2 to the power of h plus 1 minus 1, right? You can definitely check back the formula we got earlier, right? But you can take it for granted for now. So we know that the number of nodes in this case is actually equal to 2 to the power of h plus 1 minus 1. That's what we have, right? So now let's try to manipulate this equation over here. And since we got, let's simply move the 1. Let's move the 1 minus 1 to here. That means we got n plus 1 is equal to 2 to the h plus 1. And we want to really get to the property for h. Why don't we take log on both sides? In that case, we're going to get log of n plus 1 is equal to h plus 1. Right? It shouldn't be too bad for you so far. And then we can actually try to do a final simplification. Let's move the plus 1 to the other end. So that means we got h is equal to exactly log of n plus 1 and then minus 1. Okay, so that'll be the final answer. So this is indeed the minimum when h is equal to exactly this value over here. Right? So that's what we have. So this is the minimum when we have a full binary tree. And this will be the maximum when we have a one path binary tree. N minus 1 edges. Right? Which will be correspond to the height being n minus 1. Right? I think really try to understand exactly what we are talking about over here. I think these are very sound and also very exciting mathematical properties that you can really derive from the simple structure for the binary tree. You definitely want to understand these very well, so later on when we talk about algorithm, which might depend on the number of nodes or the height of the tree, you would know how to really derive the upper bound for the algorithm. Let's now move on. The final 2 measures I want to talk about, namely the number of external nodes and also the number of internal nodes. I would like to talk about them side by side for a reason. I want you to recall the discussion earlier about the number of nodes over here, because the number of nodes itself definitely include the number of internal plus external nodes. So we can definitely reuse the result and the pattern that we actually spoke about earlier. Especially in the case where we got the minimum number of nodes, that should really correspondingly result in the minimum number of internal and external nodes. Symmetrically, in the case where we got the maximum number of nodes in total, that should also result in the minimum numbers of internal and also external nodes. Hopefully you're following, right? So what I will do is I'm just going to redraw exactly like this quickly. And it will take me only 1 second to draw. There we go, right? That's one case over here, right? That's for external. And we're going to use the same diagram over here for external, internal as well. Right? We'll talk about external first and then internal. And let me just talk about this diagram very quickly. The minimum case is when we got one path tree. And in that case, we're going to get h edges, where h is really the height of the tree. And then we got h plus 1 nodes, right? That's a maximum number of nodes, including external and internal. We'll distinguish between the two kinds of nodes in just a moment. And this will be the maximum number of nodes, in which case the tree is simply full. And the same cases for internal nodes. Okay, let's now talk about an upper bound and lower bound, and then we'll visualize it and generalize it as well. Let's see over here, given a certain height h, the similar assumption as before, larger than or equal to 0. And for internal nodes, also for the h, it will also be larger than or equal to 0. And we are now talking about the number of external nodes, which will be n with the subscript e. So just recognize this convention over here. We're going to use this convention again later on when we prove some property. Similarly, when we talk about number of internal nodes, it will be n with a subscript I. N with a subscript I standing for internal. Let's see the upper bound and lower bound separately. In the case of external nodes, the lower bound is simply just 1. And the upper bound will be 2 to the power of h. Right? Let's talk about external. Why is that? In the minimum case, well, if you actually got a one path tree over here, where would be the external nodes? Well, only this one here, right? This is the only node at the bottom that has no children. Any other nodes above has exactly one child, right? So only the last node is actually external. In which case, I'm going to just highlight it, just use purple over here, right? So that's the only external nodes, right? So just 1. So this would be the general case, really. But if you talk about where height is actually equal to 3, you see exactly also the node at the bottom over here, right? So I think the general case and this specific case is really the same pattern, right? What about the maximum case? In the maximum case, the external nodes will be exactly at the bottom over here. And if you look at that over here, how many do we have at the bottom? We got 1, 2, 3, 4, 5, 6, 7, 8. We got exactly 8. And is a equal to, according to the formula, 2 to the power of h, which is 3. 2 to the power of h, which is 2 to the power 3, which would be 8. So the formula is really working. But how do we calculate in general? Well, in general, that's cannot be easier. As we said before, you can see this part over here is the bottom level of a full binary tree. In that case, as we observed the pattern earlier, how many nodes will there be in this particular level? It will be exactly 2 to the power of h external nodes over here at the bottom. Think about the maximum number of external nodes in a full binary tree is simply just the maximum number of nodes at level h. Exactly like that, right? Alright, so that's it about the explanation of the lower bounds and also upper bound for external nodes. Let's talk about the other end of the story, which is about internal nodes. And we're going to reuse the same diagram over here. And here we got the lower bounds being h and the upper bound being 2 to the h minus 1. Let's see why. Let's start with the lower bound. For the lower bound, where are the internal nodes? Let's talk about the example. Let's say we got h being 3 over here. Internal node is not is every node except for the last node at the bottom. It would be this one over here, this one over here, and also this one over here. It is exactly 3, which is equal to the heights, right? You can see exactly 1, 2, and 3. Height is actually 3. What about in general? we know that overall, given h edges corresponding to the heights, and we actually got h plus 1 nodes, including external and internal, but we're just going to exclude the final bottom node, which is external, because now we are talking about internal nodes, right? So to draw that better, I would suggest I just draw one more node. So this will be the node at level h minus 1, okay, over here. So you can think about starting from the root all the way down to and including the node at level h minus 1. You can think about this node over here is really at level h minus 1, and this will be at level h, right? So how many nodes do we have? So we got exactly, just excluding one node from h plus 1. So it would be h plus 1. Let me use purple over here, if I may. So it would be h plus 1. That'll be the max. That'll be the minimum number of nodes, and then minus 1. So this will be the bottom external nodes. Everything else will be internal, which is equal to just h, right? So that is the minimum. Okay, and did I actually highlight the minimum maximum from before? It should be 1 for the minimum for the external, and over here that should be 2 to the h for the maximum, right? Just I forgot the highlights. Let's now talk about the final case over here. What about the maximum number of internal nodes? Basically, we just don't really count the bottom row. We're gonna sum up all the nodes from level 0 all the way down to and including h minus 1, right? So what I will do is I'm going to just highlight this part over here. These are all the internal nodes I would like to calculate, right? And let me just color that quickly. These are all the internal nodes. Okay, let me just write it down. Internal nodes from levels 0, which will be the root, down to the level over here, right? Except for the bottom one, because bottom ones are the external nodes, which we don't count in this case. 0 to h minus 1, right? You can think about this level over here immediately above the last level. That will be h minus 1 level. How many are there? Let's now calculate. It's going to be the root 2 to the power of 0 plus 2 to the 1 plus 2 to the 2 all the way to the final one will be at level h minus 1, right? H minus 1. That will be 2 to the power of h minus 1, which will be equal to, right, 2 to the power of the number of turns, which will be, we go from 0 all the way to h minus 1. So that will be 2 to the power of h, and then minus 1. So this will be the maximum. Right? You really want to make sure you're very familiar with the geometric sequence formula, which I have been applying for so many times. You want to make sure you actually got it right, because if you forgot about the actual formula, you can definitely derive it from how I showed to you in the earlier part, like last week. Just make sure you don't really get, I think for the exponent, either you say h or h minus 1, h plus 1. If you got it wrong, the answer will be wrong. So you got to be very precise. Alrighty, so that's about the 4 measures we have talked about for their lower bounds and upper bounds, right? We're done with the discussion, and let's now move on to the next part.